Hello, my name is Mark Smith and welcome to our video series on getting started with inductive position sensors. This is video number 2 where we talk about how to improve your sensor design accuracy by using the auto-calibration function in the IPCE. And for this demonstration purposes, I have a linear evaluation board using the inductive position sensing technology, particularly the LX3302A IC. The part number for this board is an LX3302A L002, and plugged into it is a programmer called the with part number LXM9518. On the computer, I have the IPCE software up and running, and you can see that if I move the target, the live update data comes over nicely. Okay, before we start, I'm going to put the IC into a known state. And I'm going to load, for me, I'm going to load the default EEPROM data by hitting yes here. But you can load another EEPROM file from a previously saved state for your purposes. I encourage you to do this before you start doing your calibration. And I'm going to I'm going to do everything on the default except I'm going to put IO2 as a push-pull PWM signal, which is just PWM with a push-pull output stage. And then instead of the default PGA output for the IO2. So now we're ready to go. I'm going to go over to the measurement tab, and I recommend that you press the debug button. And what this will do is in addition to sending the output information, it will also send debug information of internal nodes from inside the IC, and our auto calibration function will use this to get the best accuracy. It's going to be able to use this information to do what's called phase and gain calibration in addition to our linearization stage. This will get you the best accuracy for the sensor. So with this, I'm going to move the target to the start of the measurement range, and I'm going to capture data, and then I'm going to go to that the next block on my graph paper. I'm using my graph paper to help me to measure the mechanical position, which I know is 6.33, and I press the capture button again, and I go over here one more to 12.66 millimeters and hit capture button. And I can do this and continue down the line and do this until we get to the end of the measurement range. I'm going to do a slightly different technique, which I will show you. As long as you capture fixed mechanical intervals, this will be an equivalent way of doing the same information. So now I'm still moving the target at fixed intervals, but I know those intervals are 6.33 millimeters, and I can just map those later if I wanted to, or all the procedures that we do today will work with fixed interval data in addition to absolute mechanical position data too. Now there's going to be some error associated with this because I'm using my eye to line the target up to the graph paper. If you use calipers or a more accurate mechanical position, you'll get the best accuracy. There's also an inflection or wraparound point in the middle here. This is due to one of our calibration parameters called the origin. It's not set correctly for this linear sensor, and the auto calibration function will also fix that too. So we're ready to go over to the analysis tab. But before we do this, I want to save the data. Now behind the scenes, that measurement tab saved the data, and the data is in this bench.xlsx file. And this is a folder under your IPCE's program directory called bench. And I'm going to load that up, and we'll save that as another file, just in case we capture data in the future, we don't override this data that we collected. Okay, so data, and you can actually see all those 15 positions we captured are shown right here. And I could map these and change these to, if you wanted to, you could just do it. Right. I can show you how to do that right now. We go like this, and then that translates that from 0 to 15 to 0 to 94.95. You also need to change this endpoint position to be the same value as the last point here, 94.95. And then we could do the same auto calibration that way, but we don't need to, and so we're not going to do that. I'm just going to show, I just wanted to show you that detail. Okay, so I'm back here. I've saved the data. We have a start and end position of 0, and we took 16 points, and the last one is 15, and we're going to map that to 0.5 volts on the output and 4.5 volts on the output. Now we recommend that you don't go over the full measurement output value of 0 to 5, because we can then reserve these voltages below 5 volts and 4.5 volts to indicate a fault. And our IC, if it detects a fault, will output, in this case it outputs a 0, but you can also have it so that the IC will output a 5 volts if there's a fault detected. And this is determined by this diagnostic polarity flag that's shown right here. Okay, and right now it's set up as logic level low for a fault. In the analysis tab, so you set those two, you come down to here, you make sure you click phase calibration. Because we collected that debug information, we can hit the auto calibrate, we can get phase. Then we just hit auto calibration. And what that's done is it will calculate the optimum values of these calibration points that are shown here to ensure that we have a straight line that matches an ideal line, and it simulated the output and then calculates what it would expect the error to be if we had collected those data with these calibration points. And it turns out it's 5 LSB, or 0.122%. Now I had a little bit of error because I'm using my eye little bit of error in the mechanical data because I'm using my eye to capture each of these points. But if you use calipers, this would represent a true error that you are seeing on your sensor. So you're ready at this stage to go ahead and update the IC settings. But let me show you on the graph one other point, is that 0 to 5 volts gets mapped over here. If I come down here, I go to this point, this turns out to be 10% of 4096, which is 409, right at that point, which represents 0.5 volts. And then the other one is 90% of 4095, which is up here, about right around 3696, if that's the right number, if my math's correct. And and that represents 90%. In this case over here, 90% is 4.5 is 90% of 5 volts. Okay, so we're ready to go. We hit the update IC settings. That brings it over to the settings page and takes all those calibration points, and they've turned red in this location. You can see the origin got adjusted, and now we hit the program, the EEPROM parameter to chip, and then the chip is done. The chip is programmed. We're also going to save this so that we don't lose those EEPROM values on our computer, even though it's on the IC itself, in case it gets overwritten in the future. Now let's go, we're really done here, but let's go back to the measurement tab and let's go ahead and check a few things. And I'm going to go to the start page and just check to ensure that inflection point has disappeared. And you can see right in the middle, it no longer is there because that origin parameter got corrected. Now, one other thing you'll notice is that we're still in the debug mode. So you do need to click that again, and takes us out of the debug mode. And then for complete purposes, let's go back to the settings page and let's save this file now instead of these EEPROM parameters that we collected. It also saves the state whether you're in debug mode or not. Let's go ahead and save it now again. And so now it's saving it in a non-debug state, depending on if you need to debug information on for further evaluation. And we'll have further videos to describe how to use that to get the best performance out of your IC, at least for debug purposes before you go into production. With that, I thank you for your time and hope you enjoy us, and I hope you join us for another video in the future on getting started with inductive position sensors.